Today we're going to do chapter 2.3 on superdense coding, and we're going to see some more uses of entanglement, some more interesting things that we can say about entanglement. So let me remind you, we've seen one of the Bell states. We've seen 0, 0 plus 1, 1 over the square root of 2. And we're going to see the other three of them today. So there are 4 Bell states, also known as EP-art pairs. I claim to you that this one could not be written as something tensor something else. It was not a separable state. We said this was an entangled state. And I want to prove that to you today. So proof of entanglement. We claimed it last time, but let me just briefly show you why it's true. And that would be to ask if this could be written in the form something tensor something else. So A0 plus B1 tensor C0 plus D1. Do you remember our definition of separable? It was just this. If a state is separable, it can be written in the form of something tensor something else. So we're asking this question, and let's see if we expand this. We're just going to come to a condition on the coefficients that will not be possible to meet. In other words, we'll get a contradiction. So you should be able to expand this using just the distributive property of the tensor products. I'm going to have AC as the coefficient of 0, 0. And then I'm going to have AD as the coefficient of 0, 1. BC is the coefficient of 1, 0. And finally, B times D is the coefficient of 1, 1. Does everyone agree? So now look what we have. We have coefficients here. They're 1 or 1 over the square root of 2. It doesn't matter. It's just the fact of what's 0 and what's not 0. So we're going to need to require the following 4 conditions on the coefficients. We need the product of AC to be equal to 1 over the square root of 2 to match, right? I'm just matching the coefficients. So A times C is equal to 1 over the square root of 2. What else do we need? A times D doesn't, there's no 0, 1 state here. So the product A times D needs to be 0. Similarly, the product of B times C needs to be 0 because that's the coefficient of 1, 0 in this Bell state. So B times C needs to be equal to 0. And then B times D needs to be 1 over the square root of 2. Does everyone see this? Just matching the coefficients. And now look what's going to happen. The product of 2 things being 0 means one of them has to be 0, right? Everyone agrees? So for example, A times D being 0 means A has to be 0 or D has to be 0. So let's just go through the cases. If A was 0, that's not going to be good because I'll never have 1 over root 2 here, regardless of what C is. You see this? Okay, so A can't be 0. Now, if D was 0, I'm going to have another problem here. So this B times D is always going to be 0. That's the contradiction that you arrive at. So this is actually sufficient. I mean, you can go through the other case as well. B times C being 0 is going to have a similar problem. You have a C here and a B here. Okay? So that's the proof that this state, which we call one of the 4 Bell states, cannot be written in this form. There's no coefficients A, B, C, and D that you can find which satisfies this. Therefore, by our definition of entanglement, this is an entangled state. Questions about this? This is a simple algebraic proof. We will build up some more sophisticated, so to speak, theoretical tools, which will give you another way to demonstrate this. But this is a completely valid proof, just examining the coefficients and using the definition of what we mean by entangled.